Okay, so let me show you how this stuff is used now. So last week, we did this little example where we had, I called this a single-phase representation of a three-phase system, and this could, since it's since it's single-phase, remember that on a three-phase basis, this would be a 1500 kVA. We were just looking at one phase. And this would be a 225 kVA. And we're going to get to that. Okay. But let's just keep in mind our two-step down transformers. Again, I said we had a 19.9 kV system. Now in the real world, that's actually one phase of a 34.5 kV distribution system, which is fairly common. 277, this would be a 480 volt transformer. And then we just did this example, we used a 240 volt transformer. Now, when we're going to use the per unit system, and this is not my complete process for using the per unit system, but it's the first two steps. What you do is you establish an S base for the entire system. Okay. When you do that, this base remains constant for the entire problem. Now, what you normally do is you choose one of the pieces of equipment. Something that you're not used to yet that we're going to look at is our generators are also going to have an MVA rating, or a kilowatt rating plus a power factor. And you can get the kilowatt or the kVA or the MVA rating of the generator just by taking the kilowatt rating or megawatt rating and divide that by the power factor. Okay. So first thing we want to do, we weren't given a generator here or a system yet that we're connected to, but we were given two transformers. And what I normally do is I take a look at the system and I choose a kVA that is usually a rating of one or more of the transformers in the system. So in this case, I would have said, and I'm going to write it here, in up above here, I'm going to write S base equal to 500 kVA, and I'm going to circle it. Now, that is the VA base, S base, for the entire system. The next thing you're going to do is establish your voltage regions. And what you do, for us, we go into a particular region. Remember last week I put a dotted line down between the transformer ratios? What that does is divides my system into voltage ratios. So I'm going to call this, like, over here on the left-hand side, 19.9 kV. In the middle here, V base 277. And here, on the right-hand side, V base 240. And I circle them so that I know what those bases are in each region. Because remember from our discussion before, then in each region we could calculate I base and Z base. But we normally don't do that until we need it. So the other thing I want to emphasize is that S base is consistent for all three phases. So all for the entire system. So I chose S base equal to 500 kVA. I'm going to write it in each of the voltage regions, but I don't normally do that. I know that my base VA is the base VA for the entire system. Okay, so that's a little peek into applying these basic characteristics or basic per unit concepts to a system, and we'll continue to build on that as we go along. Okay, so what I'd like to do now is get back into the book, and let's just begin working some small examples as it relates to transformers. Now, the first couple examples here, what we're doing is this is in case your base ratios, voltage ratios from region to region do not match your transformer ratios. It's just a couple of examples. So 5.6 here, we've got a single phase 25 kVA distribution transformer, and it has a high voltage rating of 13.2 kV and a low voltage rating of 277. So what I do is I draw the transformer, and that's how we've been drawing them. What I normally do is, because I'm familiar with one lines and how they work, is I normally just go off of a one-line diagram. And this is a 25 kVA, and it's rated, so this is why I've emphasized the difference between ratings and actual. So it's rated 25 kVA. It is also rated 13.2, so we got 13.2 kV to 277. So again, this is one phase. We're really just looking at one phase of a three-phase system. Okay? Then it says determine the low side base voltage for the following high side voltages. So what I said before is we're not going to worry so much about, if I was going to do this in per unit, I'd say, well, I got one transformer, so let's just make S base equal to 25 kVA. I don't know if I need that yet or not. But then they tell us over here, make this V base equal to 15 kV. So what you have to do is, when you have base voltages that are different than like the ratings of the transformer, you have to use the turns ratio to establish the base in the low voltage region. So V base over here would be equal to 15 kV, and we got to ratio that down to 277 over 13.2. So the base on the low voltage side then, and that should be right here, the turns ratio is 13.2 over 277. So this is the same as 15 kV times 1 over A, and V base over here then turns out to be right there, 314.8 volts, which is what they did right here, that calculation right there. And then they said, well, what if, let me do this in red then. And they said, well, what if we just let, which is the logical thing to do, what if we let V base equal to 13.2 kV in B? Okay, then V base in the low voltage region then is 277 times, it should be 13.2 kV times 1 over A. And lo and behold, you get 277. So if you choose your base ratios to be the same as the turns ratio of your transformer, then you just use the rated voltages on the transformers. And I think that's kind of the point of that exercise. Okay, now we got a three-phase transformer. Let's take a look at that. Again, I'm not going to draw all three phases, so I'm just going to use a one-line diagram representation for a transformer, and this guy is rated 400 MVA. I'm going to draw, we just got a single transformer, I think, so I'm going to draw my dotted lines through the transformer. 400 MVA three-phase transformer has a rated high-side voltage of 336.4, so it's rated 336.4 kV, line to line, and 138 kV. Let me just so it is 336.4 kV to 138 kV, which is a really strange voltage. It could be could have taps on it. Should be, the nominal rating is probably 345, but they call it 336. Okay. The transformer, the ratio Okay, so the bank ratio, we've talked about this, is 336.4 over 138. We can have the thousands if you want, but it's going to give you, right here's the calculation, 2.4377. Okay? And then it says, what if we choose V base equal to 132? And I'll just let you go through those calculations. We don't need to do this. But the calculate the base voltage on the high side for the following low side base voltages. And you'll notice here that at 138 kV, the base voltage matches the rated voltage. Okay, so same kind of thing. Where V base high side, they call it, is equal to V base low side. Now I have to ratio it up, so it'd just be times A. And that's what you're doing right here. Okay. Okay. Now I want to take us back to when we talked about transformers and non-ideal transformers. And remember we said there's one other thing here that we didn't include. It's called the magnetizing branch. But for practical purposes, when we're talking about power distribution service systems, we always ignore the magnetizing branch. If you remember it, it's because those impedances are so high. It's a parallel branch, so the impedances are really high, and that means that the current that actually flows into them is very low, compared to the rated current, which they call IHS there in Figure 5.2. Okay, so here, we start out with a transformer where we show the non-ideal characteristics. The series, we call these the series components. The high side resistance of the coil, the high side reactance of the coil, the low side reactance of the low side coil, and the resistance of the low side coil. And now I want to point out, if you remember, I calculated these R equivalent things, okay, and we transferred. So in this first example, we transferred the resistance of the secondary winding R2 into the primary by the square of the turns ratio. By the square of the turns ratio. And so here we're going from the low side to the high side. So everything goes up by the square of the turns ratio. If we wanted to show it all on the secondary side, we would ratio it down by the square of the turns ratio. So on the low voltage side, it would become R1 over A squared plus R2, and X1 over A squared plus X2. Okay? All right. Then our book gets into a couple of examples. So let's take a look at this. Single-phase transformer has a high side voltage rating and a low side voltage rating given there, 7200 to 240. The equivalent impedance of the transformer referred to the high side. So they're telling us that. Let me call it Z equivalent. Z equivalent is equal to 10 plus J20. So R equivalent equal to R1 plus A squared R2 is equal to 10, and X equivalent equal to X1 plus A squared X2 is equal to 20. So they referred everything over to the high voltage side. It says determine the equivalent impedance referred to the low voltage side. Well, all we have to do is take R equivalent. So these calculations have already been completed. R1, okay, and we just have to divide each of these by the square of the turns ratio. So R equivalent would be equal to 10 over A squared over 7200 over 240 squared. And remember, the way I always do my ratios is it's always greater than 1, so it's always the high voltage side or the low voltage side. So it'd be 10 divided by 30 squared. And if you do that calculation, it should give you 0.110111 ohms. And then X equivalent and these are all referred to the low side, equal to 20 over 7200 over 240 squared. And do that calculation, it should give you 0.0222 ohms. And so on these equivalent models then, what I want to show you then is there's two ways you could represent it. You could say put all the series impedance on the high side. Oops, doing that wrong. In which case this would be J20 and 10, or put it on the low side. And the importance in doing this is to get you to understand now the transformers are not ideal, and they do offer impedance into the system. And in some areas, that's actually a good thing. When it comes to fault currents, 111 ohms and JX equal to 0.0222 ohms. Okay, put on the low side, high side, low side, high side, low side. Okay. Now, where we're headed, I don't know if you guys remember this from machinery and controls. We'll talk about it a little bit in National Electric Code, but remember, I short circuit equal to I rated over the percent Z. That gives us the fault current on the secondary of a single transformer. What I'm revealing to you is where this all comes from. Okay, and you'll see that, and that's this stuff right here. Okay, because percent, we've been talking about per unit. Well, what is the difference between per unit and percent? Well, if I have 0.75 per unit, that's the same as 75%. Okay, and I think the next example is going to reveal to you this percent Z of a transformer, which, by the way, gets marked. It's actually stamped on every transformer because it's actually derived from tests that are done at a transformer plant. So let's go to the next one here. So we did 5.8, looking at actual ohmic impedance of a transformer. Now let's calculate the percent resistance and reactance for the distribution transformer 5.8. Do this for both the high side and the low side. So again, let me just go over here and we're going to make our per unit system. I'm going to establish an S base, and it should tell us to use, it was a 50 kVA transformer, so we're going to use S base of 50 kVA. Then on the low voltage side, we're going to let V base equal 240. Is that what it was? It was rated 240. Yep. And the high side, V base equal to 7200. Okay. Now, let's take a look here. I'm going to do example 5.9 right here. Z per unit equal to Z actual over Z base. Well, how do we calculate Z base? V base squared over S base. So Z base squared, Z base is V base squared over Z base. On the high side, this would be 7200 squared over, what am I doing here? This should be S base, 50 kVA. And now, so Z base then, what's that equal to? 7200 squared. So 7200 times 7200 divided by 50,000 and I get 1036.8. 1036.8 ohms. So Z per unit equal to Z actual over Z base. On the high side, it's 10 plus J 20 over 1036.8. And ZPU turns out to be what? Well, it would be 10 divided by 1036.8. What is that? That's 0.00965. So 0.00965 plus J 20 divided by 36.8. 0.02. 0.02. Now, I'll label that per unit ohms. That's everything referred to the high side. Let's take a look to the low side. On the low side, Z base equal to V base squared over S base, 240 squared over 50 kVA. And Z base is equal to what? 240 times 240 divided by 50, 1.15. 1.15 ohms. And ZPU equal to Z actual over Z base would be equal to 0.011 plus J 0.022 over 1.15 ZPU is going to be equal to 0.11 divided by 1.15 00957 0.00 This is probably a case where I should have let the significant digits go out a little bit more. 00957 plus J 0.0222 divided by 1.15 0.02. 0.02 ohms on both sides. And ideally, if we carried everything else significant, those two would match. And as I said years ago in one of my classes, behold the beauty of the per unit system, because that's the point. If you look at their example, and they put these into percent, so they got 0.96%, 0.96%. These are both almost exactly 0.96. And then they got 1.93. We called it 2%. So this would be 0.96%. This would be, this would actually be, this one would actually be 0.97%. We just didn't carry it out quite properly, but the J's matched up. This would be 2%. So there is the percent Z of that transformer. And that does it for these lectures on introduction to per unit. We'll pick up here when we meet again.